Good morning and welcome you all to this session of the course on fluid machines. In the last class, we discussed that the energy per unit mass, that is the head which is delivered by the fluid to a fluid machine, is given by this expression VW1 U1 minus VW2 U2 divided by G, where the nomenclature is like this: VW1 and VW2, I repeat again, are the tangential component of fluid velocity at inlet and outlet of the machine, and U1 and U2 are respectively the rotor linear velocity, which is the tangential velocity of the rotor because of its rotation, angular motion, U1 and U2 at inlet and outlet. And this we also showed can be written the same expression in a different fashion by splitting into various components like this: V1 square minus V2 square plus U1 square minus U2 square plus VR2 square minus VR1 square. Well, and where the nomenclatures are V1, V2 are the absolute velocity of the fluid at inlet and outlet of the machines respectively with respect to a stationary frame of reference. U1, U2, as I described, the rotor velocities or the blade velocity at inlet and outlet, which is nothing but the radius of rotation times the angular velocity at the inlet, and similarly that at the outlet. And VR2 and VR1 are respectively the velocity of the fluid relative to the rotor blade, which is moving with the velocity U1 and U2 at inlet and outlet. So, VR2 is the velocity of the fluid at the outlet relative to the rotor, and similarly VR1 is the velocity of the fluid at inlet relative to the rotor. And it was also recognized that these two terms, first of all this term V1 minus V1 square minus V2 square, this represents the change in the dynamic head because of the change in the absolute velocity of the fluid, that is change in the kinetic energy of the fluid, dynamic head. And these two terms is the change in the static head, means change in the static or pressure head, which is manifested in terms of change in pressure of the fluid, which is termed as change in static head or change in the pressure head. That is the flow work, that is pressure energy. Sometimes we speak loosely in fluid mechanics pressure energy, that is per unit mass, per unit weight, rather this is per unit weight, that is change in static head. So, this is contributed by the change in the static head, this is contributed by the change in the dynamic head. So, the total head that is delivered by the fluid is given by the change in its dynamic head and change in its static or pressure head, these two terms that already we discussed. Now, in relation to this, we should now discuss different types of machines depending upon the direction of flow. One is the axial flow machines. What is this axial flow machines? In axial flow machines, the main or bulk fluid, main direction of flow is in the axial direction, where the bulk fluid moves in the axial direction. There may be components of velocity in the tangential direction and radial direction, but the main motion is in the axial direction. Okay? So, this type of machines can be shown like this, axial flow machines. Let me draw this here, that let us, this is the rotor, this is the shaft which is moving, rotating with an angular speed omega. Let us, this is the rotor, and let us consider, as I have told, that rotor is a rotating disc on which the blades are mounted. This is the blades, R is the rotor and this B is the blade. The blades are mounted on it, and this is also the rotor along with the blade is rotating, they are all mounted on the rotating shaft. Now, in an axial flow machines, the flow is in almost the bulk flow is in axial direction like this. The flow takes place like this. That means the main flow is in the axial direction. That is the axial flow machines. Now, here what happens? There is a tangential component also, because when the fluid flows, so the blade is moving in the tangential direction, it has a rotational motion. So, it has tangential component of velocity, it has mainly the axial component of velocity, but the radial component of velocity is very less. That means, earlier it was shown the radial component Vf is small, it's negligibly small compared to the Va and Vw. That means, mainly Va and Vw, mainly the axial and tangential component velocities, components of velocity are there. Now, what happens here, you see the inlet and outlet of the fluid do not vary in their radial locations. So, because that inlet takes place at all radial locations, the radial location varies. For example, this is R1 inlet and this is R2 outlet. That means, from the center of rotations, that inlet, that is when this root of the blade and the tip of the blade, they vary in the radial locations, and therefore, they vary in the velocities of u. Here 1 and 2 are the inlet and outlet, the nomenclature. Now, here if we consider this as the inlet 1 and if we give nomenclature 2 out at the outlet, you see at inlet at 1 the fluid enters at from all radial locations. Similarly, at 2 at outlet, fluid comes out from all radial locations. So, therefore, you see, since the fluid velocity is assumed uniform over the entire blade height, we can say that the effect of u1, that is the effect of u, rather the blade velocity at inlet and outlet is not at all there, because at any radius you see that if you follow a particular stream, the inlet and outlet is at the same u velocities, because they are at the same radial location. So, that means the radial locations vary from root to tip, and this variation of radial location is same for the inlet and outlet flow, which is uniform over the blade height. So, therefore, we can conclude that in such cases the effect of the change in the rotor velocity is not there. Usually in these cases, the rotor velocity is defined at some mean height of the blade from the central axis, since the rotor velocity is varying from root to tip. So, therefore, for both inlet and outlet, rotor velocity is specified at a mean height. But here my intention of telling that in this case u1 square minus u2 square, this term becomes 0. That means, u1 is equal to u2. If you define u1 at a mean velocity and u2 at a mean velocity. So, therefore, this term is 0 in this case. So, in this case, therefore, h equals to 1 by 2g v1 square minus v2 square plus Vr2 square minus Vr1 square, means that the static head contributed by the change in the rotor velocity is not there, but this Vr2 and Vr1 may change, and that change is caused by a change in the area of the flow passage or cross sectional area of the flow in the axial direction. Now, in case of turbine, for turbine, what happen in case of turbines, this is H, that is the head delivered by the fluid. Turbine H is positive. So, therefore, in turbine V1 is more than V2, that means inlet fluid velocity is always more than the outlet velocity, and to get a positive contribution from this side, that is static head, we have to have Vr2 greater than Vr1, which means the passage should be, blade passage should be a converging type. That means, a converging passage will make the relative velocity at the outlet more than that of the inlet. While in case of axial compressors, where H is negative, because head or the energy per unit weight is given to the fluid. So, in that case this term is negative, and in those cases in compressors the velocity at the inlet is more than the velocity at the outlet. Okay? That means the fluid velocity is reduced, and to have again a negative term from here to contribute to the head given to the fluid, we must have VR2 less than VR1, so that this term becomes negative. So, the passages become divergent. So, therefore, in an axial flow machines, if we want to have the static head component, the blade passages should be either convergent or divergent. In case of turbines, it will be convergent to make VR2 more than VR1, and in case of axial compressors, axial flow compressors, axial flow, it will be axial flow compressors, this will be divergent to make VR2 less than VR1. But in a special case, VR2 may be made equal to VR1, which I will discuss afterwards, where there will be no contribution. That means the passage will be uniform. That means the blade passage, number of blades will be there. So, blade passages will have only uniform cross sectional area or flow area, so that VR2 is equal to VR1, and there will be no contribution from the static head at all. So, the head interactions is only because of the change in the dynamic head. Now, next another type of machine is there, which is known as radial flow machines. Now, let us consider the radial flow machines. Radial flow machines. Radial flow machines. In radial flow machines, the main direction of flow is in the radial directions. It has got very less component of axial flow velocity. Radial flow velocity can be represented like that machines, that if this is the shaft, let us have a rotor like this, and let us have a blade mounted on it, blade B mounted on it. Now, in a radial flow machines, there are two types. One is radially outward flow, radially outward flow machines. Another is radially inward flow machines. The name suggests, as you understand, that in radially outward flow machines, the flow is radial but is outward. Radially inward flow machines, the flow is radial but inward. Now, radially outward flow machines, the inlet is at a lower radius and the outlet radially outward, the outlet is like this. This is radially outward flow machines. This is outward flow, radially outward flow. Similarly, in a radially inward flow machine, what will be the picture? Radially inward flow machines, if you like to show this or we like to show it, radially inward flow machines like this. This is the rotor, this is the rotor. So, radially inward flow machines, if it is the blade, this is the blade, then radially inward flow machine just the opposite. That means, the fluid inlet is at a higher radius and comes by a lower radius. That means, it is inward. Inward and outward means away from the center of rotation, inward means towards the center of rotation. So, for inward flow machines, the fluid inlet, this is inlet 1, this is this is inlet 1, this is outlet 2, inlet 1, out. Inlet and outlet are given by the suffix 1 2, given by the suffix 1 2. For an inward flow, the inlet is at a higher radius and comes radially inward and goes out at a lower radius. So, here what happens? The fluid has substantially VW and VF, that is the flow velocity or the radial component of velocity, as I have shown earlier. So, here VA is very small, VA is very small. Now, you see in this case what happens? In this case, V1 minus V2 square by 2, this dynamic head is there. Change in static head, U1 and U2, this component due to change in rotor velocity or blade velocity is very much there, because U1 and U2 are varying, U1 and U2 are varying, because the inlet and outlet is at different radial position from the central axis. Now, VR2 and VR1 I will come afterwards, that depends upon the change in the cross sectional area of flow or flow passage. Now, with respect to U1 and U2, you see for a outward flow, U1 is less than U2. This is because this is at a lower radius of rotation. U is omega into R. So, if this is R1 and the tip radius is R2, root radius is R1 and tip radius is R2. So, here what happens? The tip velocity is more than the root velocity. So, here what happens? The U2 is greater than U1. Okay. In this case, U1 is greater than U2. Now, consider a turbine. In case of turbine, consider a case of turbine. Now, in case of turbine, we want this thing to be positive, because turbine head is delivered by the fluid, and this is the expression for head delivered by the fluid. So, this is positive. In case of turbine, V1 is more than V2, as I have told. So, if you have a positive value contribution from the centrifugal head, which is manifested in terms of static head, U1 has to be more than U2. So, therefore, for a turbine, this will be radially inward flow. This is for turbines. This is for turbine. That means, for turbine, it has to be radially inward flow machines. The machine should be radially inward flow machines. Why? Because if radially inward flow, its inlet U1 will be more than the outlet U. That means, U2 is less than U1, U1 is greater than U2. So, this will be positive. But in case of a pump or compressor, this is the head given to the fluid. So, all this will be negative, this term will be negative, all the terms will be negative. V1 is less than V2. So, that this is negative. Similarly, for a pump or compressor, U1 and U2 should be such that this contribution should be negative. That means, U1 should be less than U2. So, in this case, the fluid should flow radially outward. So, that the inlet U will be lower than the outlet U. That means, here you see U2 is greater than U1, or you can write U1 is less than U2. So, this is negative. So, therefore, for a pump or turbine, for a pump or compressor, the machine should be radially outward flow. Now, it is clear radially why the turbines are radially outward flow machines and the pumps are made radially inward flow machines. Now, along with that, the velocity, relative velocity change also, if you see, in case of turbine, we also want a positive contribution from this. So, VR2 has to be more than VR1. So, for a turbine again, VR2 has to be greater than VR1. Why? Because again the same logic, that this should be positive. This head should, static head should be positive. That means, the flow passage should be convergent one. That means, the blade should give a passage like that, the rotor blade. When for a turbine, this is coming like this, radially inward flow, it should go like that. A converging passage will increase the velocity relative to the blade. So, that VR2 is greater than VR1. So, for a pump or compressor, it is just the reverse. So, therefore, for a pump or compressor, we want a negative value in this to have a contribution from this. All the terms should be negative. So, that H will be additive by the 3 terms. With a negative sign means the head is given to the fluid. So, therefore, negative this means VR2 will be less than VR1. So, VR2 will be less than VR1. In that case, the pump should be a diverging type. That means, the radially outward flow. In this case, sorry, this diagram is wrong. So, this should be the same diagram, but the flow is radially outward. So, in the direction of the flow, the passage is diverging. In the direction of the flow, this passage is converging. So, therefore, our conclusion is that for a radial flow machines, there will be static head contributed by both the component, the centrifugal component, change in the rotor velocities plus change in the relative velocity of the fluid along with the change in the dynamic head. And for a turbine, this is radially inward flow machines and the flow should be in a convergent passage, the blade passage should be convergent in the direction of flow, so that both the terms should be positive. Similarly, in case of pumps or compressor, it will be radially outward flow, that means this term should be negative, and at the same time the direction of the flow along the direction of the flow, the blade passage should be diverging, so that we get this part also negative, so that all the terms are additive and contributing together simultaneously in the head interactions. That means, head given to the fluid or head given by the fluid. So, this concludes the discussions on axial flow and radial flow machines. Now, I will come to a very important thing, impulse and reaction machines. Impulse and reaction machines. Reaction machines, impulse and reaction machines. Now, again I will write the same expression, that H is 1 by 2g. Let us write again this same thing, V1 square minus V2 square plus again U1 square minus U2 square plus VR2 square minus VR1 square with their nomenclatures as defined. And this is the change in dynamic head. Again I am writing this thing, because this formula is very important in understanding all the fluid mechanical principles, and these two terms together is change in static or pressure head, static or pressure head, static or pressure head. Okay. Now, there are machines where the static or pressure head is 0 while the fluid flows through the rotor, and the head delivered by a turbine is given, if you consider turbine, head delivered by the turbine is given only by the change in the dynamic head. Those machines are known as impulse machines, where the change in the static and pressure head is 0. There is no change in the static or pressure head in a fluid machines. Now, let us understand this thing in this way. Let us consider a turbine. Now, in general, a fluid machines, for example, turbine consists of a stator S and a rotor R. S stands for stator and R stands for rotor. Now, fluid first enters into, stator is a fixed component, rotor is the moving component. Here I am using the block diagram in sequence of operation to show stator and rotor may not be side by side. It depends upon the flow configuration. In an axial flow machine, stator and rotor may be side by side. In a radial flow machine, stator may be above, radially above or radially below the rotor, which is rotating. That depends upon the flow directions, radially inward or radially outward. In an axial flow machine, it should be side by side. But one thing, stator is always fixed to a casing, fixed casing, but rotor is fixed to the shaft or the rotating drum. So, rotor is in motion. So, fluid first enters in stator, consider turbines, then comes to the rotor. So, in that sequence of operation, I show this, first come to the stator and then to the rotor. So, first fluid enters in case of a turbine to the stator, the stored energy of the fluid, which may be in terms of its pressure, in terms of its thermal energy, in terms of its intermolecular energy because of its temperature, whatever may be the case, that is first being utilized in stator to create a high velocity, a kinetic energy of the fluid along with a pressure, along with a high pressure. Now, here one has to understand that if we want there should be no change in the rotor, if we design a machine where in the rotor there will be no change in the static or pressure rate, there are two ways we can do it. First, we can exploit the entire stored energy of the fluid at the inlet of the stator, which comes in the form of fluid pressure or fluid temperature, in kinetic energy, utilizing its entire pressure, so that the pressure is to the atmospheric pressure. That means, we totally expand the fluid up to atmospheric pressure and we make the rotor open, so that there is no change in the pressure, the entire pressure is atmospheric pressure. Another way we can do it, that we may not expand it up to atmospheric pressure in the stator to exploit the stored energy of the fluid. In that case, we have to make a casing in the rotor, since the fluid is at a pressure higher than the atmospheric pressure, but the flow passages should be made such that the fluid pressure should not change, and it has to be an axial flow machine, so that U1 and U2 changes should not be there. So, two ways we can think of such an impulse machine, but in a reaction machines, both the kinetic energy change or change in dynamic head and the static or pressure rate changes in the rotor. That means, the stator should not expand up to atmospheric pressure, and moreover the flow passages should not be uniform. That means, flow passage should be convergent or divergent to make a change in the relative velocity. So, therefore, with this concept we see that impulse machine must have two things, that impulse machine, that is the flow area has to be constant, or it should, that means it should be open if the fluid is expanded up to the atmospheric pressure, so that the impulse machine will work on this. But a radial flow machine is always act as a reaction machine. This is because even if you make the flow area constant in a radial flow machines to make VR2, VR1, but U1, U2 you cannot eliminate. So, therefore, this thing is inevitable, that change in the centrifugal head. So, therefore, all radial flow machines, all impulse machines are usually therefore axial flow machines, or there is another machines, tangential flow machines. They cannot be radial flow machines, tangential flow machines, which I will describe afterwards. But reaction machines are always radial flow machines. Reaction machines are always radial flow machines. Okay? Reaction machines are always radial flow machines, because this is inevitable. But nevertheless, a theory you can tell that this may be counterweight. For example, you can make a fluid like this, where if we make it like this, that this is flowing in such a way that change in the U1 and U2 and VR2 and VR1 counterbalances each other. That means, if U1 is greater than U2, that means this is positive, and VR2 is less than VR1. That means, this is negative in a way that they balance together. That means, what you have to do, U1 is greater than U2 means that your inlet will be at a higher radius than the outlet, and VR2 is less than means not this one. Then we have to design like this, a diverging passage and a radially inward flow, that is 1 and 2. In this case, U1 is greater than U2, VR2 is less than VR1. In such a way the passage will be designed, they counter each other, or the opposite, U1 is less than U2 and VR2 is greater than VR1. That means, the same passage with a opposite direction of flow, radially outward. But these things have never been done in practice. This cannot be done because of this thing in the independently contributing the change in static pressure rate. All radial flow machines are reaction machines. So, that is the difference between impulse machines and reaction machines. And let me show you an example of a reaction and impulse machine. Let me show you an example of reaction and impulse machines. It is a good example that you see. This is an example of reaction and impulse machine. You see a paddle wheel which is rotating, this type of paddle wheel, this is rotating shaft and these are the blades of the paddle wheel. A nozzle is fixed by through which a water jet is directed and is impinged on these blade surfaces. The nozzle is fixed, the liquid, for example water, enters at high pressure. What is the function of the nozzle? They convert this pressure into high velocity water jet, and by impinging the jet impinges and flows along the blade and ultimately comes out with a low velocity and this blade rotates. So, here what happens? This is the rotor, the paddle wheel is the rotor and we can consider nozzle as the stator. So, nozzle converts the stored energy of the fluid in term of pressure at the beginning to a high velocity jet, whereas while it flows through the rotor, the work is done by the rotor or energy is delivered by the fluid to the rotor simply by the change in the dynamic head, because there is no question of pressure change, pressure is already atmospheric. That means, this has expanded, the nozzle as stator has expanded the fluid up to atmospheric pressure. This is a good example of a impulse machine, paddle wheel as an example of impulse machine. Similarly, on the other hand, you see a lawn sprinkler. What happens here? The entry of water comes at high pressure and goes through the two arms, straight arm of the sprinkler, at the end of which there is a nozzle. There is a nozzle, which is these nozzles are converging nozzles, this converging type of area. So, these nozzles are converging passages. So, what happens when the fluid passes through the nozzle? It changes its pressure to the ambient pressure, changes its pressure and comes out at high velocity. And because of the change in this angular momentum, if you make it free, the lawn sprinkler will rotate and you will get mechanical power. So, in this case what happens? The entire sprinkler acts as a rotor, because this is rotating and developing power, and this nozzle being a part and parcel of the rotor changes the fluid pressure. So, therefore, both the change in the static head and dynamic head takes place while the fluid moving through this rotor. So, this is an example of reaction turbine, lawn sprinkler as an example of reaction turbine. Okay. And at the end I will tell you, in a impulse and reaction machine, to differentiate these two, any machine we define a degree of reaction, we define degree of reaction as R as the ratio of the change in static head. That means 1 by 2g change in the static head, u1 square minus u2 square plus Vr2 square minus Vr1 square divided by the change in the total head. Total head is what? It is 1 by 2g V1 square minus V2 square plus U1 square minus U2 square plus Vr2 square minus Vr1 square. Now, for any reaction machine, all these three components are there, but for an impulse machine this is not there. That means, for an impulse machine numerator is 0. Therefore, for an impulse machine, the degree of reaction is 0. But for a reaction machine, degree of reaction is not 0, because this part is there. So, how much of the total head delivered by the fluid is being contributed by the static head is the definition of degree of reaction. So, for an impulse machine, the degree of reaction is 0. So, for any reaction machine, we specify it by the degree of reaction, and accordingly we design the stator and rotor blades. Okay.